the ground so that we have plenty of time for Q&A towards the end. We have an exciting run up here today. This is our 12th webinar for NHABON. I think many of you are newcomers or have been coming for a long time. Some of you are newcomers. I was thinking as I was putting this intro slide up that we do something called the NOAA West Watch webinar on the West Coast a lot to brief NOAA on all things oceanographic. And they always do a poll at the beginning, you know, is this your first time? Are you a repeat customer? Maybe we should start doing that because I'd like to get a sense of how many people are new to this webinar. We do give some of the same slides at the top of the hour each time to give you some sense of what NHABON is about. And it's good to know, but we're really excited for the turnout. This one is titled The Role of Satellite Observations in NHABON and Exciting Advances in Space-Based HAB Detection. Next slide, Masha. Thank you. So I'm Clarissa Anderson, and I'm a co-chair of this community of practice along with Dr. Quay Dortch, and we're both here today. We are chairing this. I'm going to do a little bit more of the intro today just to get us familiarized with what's going on with satellites and why we chose this topic. I have a very irritated greyhound outside barking at me, so I may have to deal with that in 1 minute. I'm sorry. But today we have some great speakers, and we're going to delve into this topic of satellites that I think we've done a bit in the past, but never like quite this targeted. So we're going to have Susanne Craig, Andrea VanderWoude, and Raphe Kudela, not in that order. We'll show you the actual order in just a minute. And before we go there, I just want to remind you all what NHABON is about. So next slide, please. So this is our vision and our mission. Pretty simple: sustained national network for regional HAB observing. We're trying to codify this view of a national infrastructure surrounding HAB detection, monitoring, and prediction that isn't just regional, it's not provincial, it's not one-offs, it's really more about how do we come together and do this right, do it in a way where we're sharing information, sharing experiences, and bringing that learning together into this community of practice. And so that's a big push behind this, but then of course there's a component that's financial. We want to have a congressional we want this to be a reality from Congress's point of view. We want to get this into some of our authorizations and have some of this really stand the test of time and become a sustained program within NOAA and also at the interagency level. Next slide. So you've seen this before. This is this circular feedback loop of what it means to have a true observing network where the OBS, the data integration, the modeling are integrated, they're communicating, and they're driving synthesis and products for decision making that's driven by the societal need. And we've talked a lot about OBS. We talked about in situ OBS. We haven't talked too much about remote sensing as a really important component of observations. And that can be airborne remote sensing, that can be satellite-based remote sensing. So we're going to talk about that more today with 3 people who know quite a lot about it. And so we're excited to get into that. Next slide. Here are our speakers, and I'm going to introduce each of them real fast before we move on to Suzanne's first talk. So Susanne is a senior scientist at NASA Goddard Space Flight Center's Ocean Ecology Laboratory. I'm excited to introduce her. She's been a good friend for a very long time. She is importantly now the science lead for PACE. You're going to hear a lot about PACE, the new science mission, new operational mission now at NOAA, which is and she's part of the system vicarious calibration team. Her interests range in phytoplankton ecology, development of autonomous measurement platforms, as well as dogs and lifting very heavy things for fun. We're going to have to ask her more about that at the end. Dr. Raphe Kudela is a distinguished professor in the Ocean Sciences Department at UC Santa Cruz, very important mentor to me. He's has been a member of NHC, NHABON, Global HAB, TRENS-PO. I think you forgot the Goose Bio-Eco panel and everything else that goes along with that, and many more things. GeoHab before Global HAB. Raphe is many things. His bio is short, but his legacy is long. And Dr. Andrea VanderWoude is a remote sensing research scientist under the Observing Systems and Advanced Technology Group at NOAA's Great Lakes Environmental Research Laboratory. I usually never have to say GLERL out loud. That's really hard. And acts as the NOAA Coast Watch manager for the Great Lakes. So there at GLERL, she's managed the hyperspectral imaging program in support of the EPA Great Lakes Restoration Initiative interagency funding for the past 8 years to monitor cyanoHABs throughout the Great Lakes. And her origin, her field, she's biological and a satellite oceanographer for the PhD from UC Santa Cruz. That was with Raphe, and is also a geologist with a bachelor's from Michigan Technological University. So we're going to move on to the talks. I'm really excited that we have this lineup. And as before, just a reminder, you can always put your questions into the Q&A and chat panels. We'll revisit the questions at the end. We're just going to try to go seamlessly across the 3 talks, let everyone get their information out to the community, and then we'll hopefully have somewhere along the lines of 10 minutes for discussion towards the end, and we may go over the hour a little bit, but we really will try not to. And we'll loop back to a little bit of announcements and housekeeping at the very end. Okay, so Susanne, please take it away. I think you'll be able to share your screen now.
Okay, thank you, Clarissa, and thank you for the invite to speak here today. HABs are a topic near and dear to my heart, and I'm really glad to be kind of looping back into the HAB world again. So next slide, please. Oh, yeah, and then another click. We got lots of clicks. NASA has lots of clicks and lots of animations. There we go. Okay, so I'm going to talk to you today about the PACE mission. The PACE mission is our newest Earth observation mission. And if you could just click that slide there, Masha, I want to show you what it looked like when we launched in her up into space.
6, 5.
This is
4,
Kennedy
3,
Space Center,
2,
February 8th
1.
of this year. Many of us attended. Engineers, and this is the PACE satellite taking off on top of a SpaceX Falcon 9 rocket. I know we use this word awesome a lot, but it really was pretty awesome. We heard the sonic booms, we felt the rumbles. This next little bit of footage here is, this is PACE actually inserted into orbit, and the PACE spacecraft is separating from the launch vehicle. This is it making its way off. You'll see in the kind of 2 o'clock position, there's 3 horizontal lines. Those are the solar arrays that unfurled themselves beautifully like a beautiful butterfly once she had inserted herself into a stable orbit. And we all sat with bated breath waiting for this. So yeah, again, as I say, awesome is an overused word, but for the hundreds and hundreds of PACE engineers, scientists, and their families that supported them, this was truly the kind of a peak of all of those efforts over 20 plus years, really 20 plus years. Okay, so that is those are the glory shots. Next slide, please, and thank you. Okay, so what is PACE going to do? PACE is going to do many things. It's a multi-discipline mission, but from our perspective as phytoplankton ecologists and HAB aficionados, PACE aims to see the microscopic from space. Next slide, please. I'm sorry, there's a little lag in my end, so I'm sorry if there's a gap. Okay, and then one more click, Masha, and this will start the animation. Thank you. Okay, so just a little bit about PACE oh, back one, please. Okay. And then a click to start the animation. Oh no. If you hover over the thing, there you go, you'll get the play bar. There you go. So we are going to be studying ocean biology, clouds, aerosols, that real kind of system of systems. And of course the land as well. PACE is a polar orbiting, ascending sun synchronous satellite. It passes over each area of the Earth at approximately local solar noon. On board, the instrument that we are interested in is the Ocean Color Instrument, or OCI. That's a hyperspectral scanning radiometer, scanning from the UV visible and into the near infrared and SWIR bands with a hyperspectral resolution. It gives us a 1 to 2 day global coverage and a spatial resolution of 1 kilometer squared nadir, meaning when the satellite is looking straight down at the Earth's surface. Okay, next slide, please. So as I said, the PACE mission, It's going to facilitate a lot of aquatic and oceanographic research. Some of those aquatic applications are covered here in this slide, and they include the management and the understanding of phytoplankton community composition, harmful algal blooms, of course pertinent to today's talk, as well as the knowledge and information that we need to provide management for fisheries and aquaculture, ecosystem and watershed health, and of course the coastal tourism industries that rest upon the integrity of all of those systems. And what we're showing here in this animation is actually model output. This is aspiration. This is aspirational for us, what we ultimately want to achieve. We're showing there 4 different classes of phytoplankton and how they evolve through a simulated time span. And this is really what underpins the biological imperatives of the PACE mission, trying to get from those bulk estimates of chlorophyll that we've traditionally relied upon in the past, and using the hyperspectral signal to help us resolve community composition. And of course, that includes harmful algal blooms. Next slide, please. So how do we do that? Next slide, please. I just want to do a little ocean color 101. Not everyone is a photon geek like me, but let's just remind ourselves what ocean color remote sensing is. So the color of the ocean is determined by the interactions of the incident light with the optically active constituents in the water. So the color is a function of both what's in the water and the quality of light that is incident upon the water. And one more click, please. We've got a couple little animations. So we've got our little happy photon there. Next click, another click, please. And then that little happy photon can undergo 2 fates. It can either be absorbed or it can be scattered. And one more click for the next animation. And what happens is that some of that incident light is reflected off the surface at the critical angle, but some of it actually penetrates the air surface interface, interacts with the water and its constituents, and then can be scattered in the backward direction. And one more click, and our resulting little happy photon then contributes to water leaving radiance that impinges on our lovely eyeballs. One more click, please. But if you are above the Earth, the eyeball is actually the satellite. So this is what the satellite is seeing. The satellite is seeing that water leaving reflectance, but that, remember, that's contained within the contribution of the Earth's atmosphere as well. So we've got a tiny little bit of water leaving radiance plus a whole lot of scattered light from the Earth's atmosphere. One more click, please. So the take-home message from this is essentially the core satellite data are accurate measurements of light intensity from the UV all the way through to the shortwave infrared wavelengths. And it's that spectrum of electromagnetic information that we use to derive all of those products that some of you are probably familiar with. Next slide, please. So what I want to kind of illustrate here is how now we're moving from legacy multispectral radiometry to essentially true spectroscopy. What you see here is a little table with the electromagnetic spectrum, a portion of it from the UV through to the SWIR bands, and those 4 different columns correspond to all of our legacy and current ocean color sensors, ranging from CZCS in the late 70s all the way through the CWIS and MODIS era, right up to the current VIIRS era. And what you'll notice is that they have little horizontal bands, and those bands correspond to the part of the spectrum that those instruments measure ocean color at. So they are only able to measure ocean color at a handful of bands. It's like having the rainbow represented by, like 8 to 10 crayons. One more click, please, for the next figure. In contrast, the PACE mission is hyperspectral. And what that means is that it makes continuous measurements of that electromagnetic spectrum, that reflected light. So instead of having 8 to 10 crayons, we have hundreds and hundreds of different crayons with all of the subtle nuances of color in there. So a couple more clicks. Why do we want to have this hyperspectral information? Yeah, so I want to show a couple of examples as to why it's important that we have more spectrally resolved information. One more click, please, Masha. Thank you. We're big on animations in our visualization studio. There we go. So if we take a couple of examples, so two different families or classes of diatoms, one which is essentially turtle food, one which is essentially fish food. If you are a VIIRS satellite, that's kind of hard to say, you would have an absorption spectrum at those discrete bands, and you wouldn't really see much difference between the red dots and the black dots. You'd see a bit of a difference in terms of the amplitude there out at 550. However, if you're a PACE satellite and you've got those hundreds and hundreds of crayons to represent the water-leaving radiance, we now begin to see how we can home in on the spectral differences, the optical fingerprints, if you like, with that hyperspectral resolution. So that is why we aim to have this hyperspectral mission. Okay, next slide, please. Okay. So that's PACE. I just wanted to give you a kind of a 10,000-foot view. What I would also like to draw your attention to is an upcoming mission. This is called GLIMMER. GLIMMER is what we call an Earth Venture Instrument mission. It's likely to be launched sometime in the 2025 to 2026 period of time. In contrast to PACE, GLIMMER is a geostationary satellite, meaning it does not rotate around the Earth, but rather its orbital mechanics are set up in such a way that it images the same point of the Earth. So it turns with the Earth and constantly images the same regions, fields of regard. And for GLIMMER, the fields of regard are essentially the continental US, focusing on the west and the east coast, and of course the Gulf of Mexico, which is a big hotspot, as we know, for harmful algal blooms. We'll also have some capability to look at the Great Lakes region, as well as some other regions along. You can see there in the little schematic. Okay, so GLIMMER is again going to be another kind of tool in our arsenal going forward. It has not yet launched, but we should be aware of that as a community. Next slide, please. Another upcoming hyperspectral mission is going to be GeoXO. This is a mission co-led by NOAA and NASA, and on GeoXO is the OCX instrument. That's the next generation of hyperspectral instruments. Again, GeoXO is going to be a geostationary satellite. Again, it will look at the west and east coast of continental US, as well as the Gulf of Mexico. Next slide, please. And what I'm going to show you here in this next slide is, you don't have to read it all, but just some pertinent kind of take-home messages is that it is a geostationary satellite. It is hyperspectral. You can see its wavelength range there with its spectral resolution. It has a spatial resolution of 300 meters and a revisit time of 2 hours, meaning that you get a new image of those fields of regard every 2 hours. Its launch date is anticipated to be something in the 2033 range. So that's a good long time from now, almost a decade, but this is how long these missions take to plan. Next slide, please, Masha. Okay, so apologies to all of the techies in the audience, but I just wanted to reinforce this idea of engineering trade space. And that concept is essentially, you can't have all the things all the time. And I want to just highlight the differences between two of those instruments that I spoke about, one being PACE, one being GLIMMER. PACE gives us 1 kilometer spatial resolution, which for HABs and lots of other aquatic processes is actually quite coarse. Oh, my dog has come to say hello. You're going to see a dog head plop in. Hi. So it's quite a coarse spatial resolution. However, it gives us 5 nanometer spectral resolution with a 2.5 nanometer sampling size, and it has an excellent signal to noise ratio. It's got an 1800 signal to noise ratio, and it gives us an entire global coverage within 1 to 2 days. Contrast that with GLIMMER, which has a much higher spatial resolution, 300 meters, slightly coarser spectral resolution, a much lower signal to noise ratio, but the pro for GLIMMER is that it's going to give us hourly imagery for discrete regions of the globe. So the take home is you just can't have it all. This is why PACE has a larger pixel size, because it has to average more incident radiation on its sensors to get that excellent signal to noise ratio. So that was just something I wanted to point out. Next slide, please. And here are some images from the first few days of when we actually switched PACE on. We had a 3 to 4 week period of commissioning where we checked out the instrument health, spacecraft health, and then we turned on the sensors. And this was a kind of magical moment. We got absolutely excellent data within the first few days of turning on our sensors. What you're seeing here in these little slices, if I start from the left-hand panel, first of all, I'll geographically situate you. This is the South African coast. That bluey green slice that you're seeing, that's a true color image. And you can see some beautiful structure there in the water. To the right-hand side, that little blue RGB colored imagery, that is the chlorophyll algorithm applied to that first light imagery. So we're seeing the chlorophyll concentrations. And the thing that I really want to home in now is this middle slice of imagery, those greens and pinks. This is actually an algorithm called the Moana algorithm, currently being tested out on our systems as we speak, and soon to be made very available to the public, that is able to resolve the abundance of pico, eukaryotes, and synechococcus. This is based on an algorithm developed by a postdoc in our lab who has since left, Dr. Priscilla Lang, who was kind enough to include me on that paper. So we're actually implementing Moana. So that's hinting at those aspirations that we have, and we have other phytoplankton community composition algorithms that are currently in the production phase. They're coded up and in our processing system. Okay, and next slide, please. I now would like to share a couple of slides from my wonderful colleague, Dr. Morgane McKibben. She is the PACE applications lead. And this is to reassure you that PACE is very much concerned with being involved in HAB research. Morgane has put together a slide here just to illustrate the kind of breadth of HAB research that PACE is currently involved in. These are projects that take place worldwide in large inland lakes, coasts and estuaries and the open ocean. We have a list there of the PIs involved and a little short title of their research projects. So PACE will be very much involved in feeding information to the HAB community, and we really hope that we can be here for you to provide those products that help you with your HAB research and for monitoring as well. Next slide, please. Oh, Google Chrome. Yeah, next slide, please. Thanks. And this is just a plug. Morgane asked me to distribute this to you. You can take a moment and maybe snap that with your smartphones or take a screenshot. Just to draw your attention to it, that if you are going to the AGU meeting in fall of December 24 here in Washington, DC, US, you can go along to the workshop, the PACE applications and workshop, and that is with all of our early adopters, our PACE science, satellite science and applications team, along with all of those early adopters and community of practice people. A lot of those folks will all be represented at that workshop. With that, I just want to finish off with some closing thoughts. I will be finished in a jiffy, Clarissa. So next slide, please. So I'll leave these closing thoughts and kind of things for us all to ponder as a collective community. We know that retrieving the water leading signal over the waters that we're interested in as HAB researchers, those are usually coastal and inland waters, can be very challenging for lots of different reasons, but primarily atmospheric correction failure or algorithmic failure. We really need to establish and develop new approaches to overcome these challenges. We want to fully exploit the information contained in those hyperspectral signals. That is more than likely going to involve some degree of machine learning and more sophisticated training data to train those algorithms. So instead of being purely pigment-based, we want to move to things like using imaging flow cytobot, taxonomic information, omics, plus other environmental data. And not to state the obvious, satellites can't see through clouds. So in order to have a truly Earth system approach to observing and understanding HABs, we need to more fully utilize these autonomous technologies such as UAVs, gliders, moorings and profiling flows. And with that, I will stop and pass you over to our next speaker. Thank you for your time.
Thank you, Susanne. That was really great. As I said before, we're going to hold questions. Let's move over to Rafe's talk now. I see a few coming in. They're all excellent questions. We will return to those, I promise you. All right, so Raphe, whenever you're ready, take it away. Thank you.
All right, thanks, Clarissa. So yeah, so I'm going to talk a little bit about some of the things Susanne mentioned, and you're probably all familiar with the technology readiness level idea that both NASA and NOAA use. And I'm going to start at the top with operational systems and then work our way down to some exciting things that we could do in the future with remote sensing. So next slide, Masha. And so one operational system that you're probably quite familiar with is the CYAN network. And so this takes advantage of satellite data and the fact that if you have the right bands, you can pick out the phycocyanin absorption feature. And that lets you pick out blue-green algae or cyanobacteria in water bodies. And so here is just an example. This is San Francisco Bay from last week or a few days ago. And you can see everywhere there's black, the satellite can see that, and the black just simply means that there were no cyanobacteria at the moment. If you kind of squint, you can see there's a little bit of color in there. But to the right, I showed from the same 10-day window, that's Clear Lake in Northern California. And Clear Lake almost always has blue-green algae blooms. And so you can see this sort of resolution you get from the CYAN products. And so this is truly operational. It's producing these images nationally. It runs 24/7. Here in California, the California Water Boards and San Francisco Estuary Institute have built their own portal on top of CYAN to provide information in real time to users that are interested in that. And if you see that little yellow box kind of over to the right in the left-hand image, that is gray because the satellite can't see it, that it doesn't have the spatial resolution to see what's there. And so the next slide, we're going to zoom in on that. And that's where that little box is looking at. And so this is a place called Discovery Bay, California. And as you can kind of tell, it's man-made. It's a series of channels of water with very beautiful houses. Everybody has their own dock, their own access to the waterways. But you can't see it with this standard product because they're using a satellite called Sentinel-3 that has ULCI, has 300-meter resolution, and Discovery Bay is just too small. You can't distinguish the features even though you could see it in something like Google Earth. And so next slide, please. And the reason we care is Discovery Bay is one of the places in California that pretty much has annual blooms. And so this was from this past summer in July, and you can see beautiful bright green water that happened to be also incredibly toxic. And so it's a little bit frustrating for people that are living in those areas when we say, well, these satellites can see cyanobacteria blooms all over the world. And they say, well, you can't see mine, and it's not helping me. And so we've been trying to figure out if there's a way that we could move beyond the operational product into something that I would call semi-operational, and you'll see why, to improve our ability to distinguish these smaller water bodies. Next slide, please. And so what we're using is an algorithm we developed several years ago called the scattering line height algorithm. And so unlike the CYAN algorithm that's looking for phycocyanin, instead we're looking for a really bright scattering signal that's associated with surface forming blooms like microcystis and aphanosomena. And so here we're looking at Discovery Bay again from a satellite. This is using Sentinel-2, and so we can get down to 10-meter resolution. On the left is the true color image. This is what it looks like if you flew over in an airplane. The middle is that SLH. Red means that there's big surface forming scums on the water. This sort of bright green means that the scums are starting to build up and you're probably going to have a problem. And then on the right-hand side is a chlorophyll product. And so one thing you can see really quickly is that the chlorophyll is kind of blue everywhere that's not in that red area. And because it's not picking out the intensification of these blooms that we get from scattering line height. And if you're wondering, that sort of bottom right corner, that's a golf course, which is why it doesn't change color depending on the algorithm. And so this is what we can do by simply taking a different satellite and a slightly different approach, and coming back to Suzanne's point, choosing the bands that you want to use. Next slide, please. What we're pretty excited about is, in partnership with San Francisco Estuary Institute, we've been able to take that scattering line height algorithm and essentially automate it in Google Earth Engine. And so here what you're looking at, the map with the funky colors, those are areas of interest that we drew on the map. And then we can use Google Earth Engine to query all of the historical data. And so here we're showing about 2 years worth of data that's been turned into scattering line height. And you can see really nice patterns, like we tend to get these blooms in the middle of the summer. They recur year to year. But once it's in Google Earth Engine, you don't need to download all the data yourself. We can make this into a web app. Anybody can use it. You could draw your own polygons and pick out your favorite water body. And again, we can get down to about 10-meter resolution with this. Next slide, please. And so that was one example of going from sort of a research product to a semi-operational product where we're running it in Google Earth Engine. Another one, we of course use chlorophyll all the time in HAB observing and within HAB observations networks. And another bloom that occurred in San Francisco Bay, this was summer of 2022. And so on the left, you're seeing San Francisco Bay, the reds are high chlorophyll, the blues and greens are lower chlorophyll, and then the white out in the ocean is just cloud cover. But we had a massive bloom of a rhaphidophite called Heterosigma akashuo, and it was producing very, very large fish kills. And so there was a big attempt to get out there and respond to it and see where it was coming from, where it's going, what's going on with that. And so fortunately for us, Rick Stumpf at NCOS started sending satellite imagery almost immediately, saying, I think something's going on in your area, because he keeps track of interesting events throughout the country. Next slide, please. And we were able to go out there and get lots and lots of observational data with USGS and SFEI and some other partners. And we were able to test some of the standard operational products. And so on the left, that panel A, that is the standard NASA processing. And I would argue that that looks like a shotgun graph and that it's not really telling you anything useful. And so the satellite is basically a very poor predictor of chlorophyll if you were just using the standard NASA product. On the right, we ran it through the European Space Agency product instead. It's a little bit better, but I'll just point out that it flatlines. And so the satellite basically tells you that you don't have chlorophyll higher than about 20 micrograms per liter. But in the field, we were seeing it going up well over 100 micrograms per liter. And so next slide, please. And so again, you can fix that. And so what we did is we took all that data and we modified an algorithm that Rick Stumpf had developed for the Chesapeake Bay. And so this is the NOAA NCOS operational algorithm, but it hadn't been tuned for San Francisco Bay. And so we were able to go in and adjust it. And so on the left, what you're looking at is now it's the in situ chlorophyll on the x-axis versus our modified algorithm on the y-axis. Blue, greens, and reds are just showing you low, medium, and high chlorophyll. And on the right, if you're familiar with these, this is a quantile plot that shows you biases. And so we're doing really well up to about 20 micrograms per liter. It's on the 1-to-1 line. We tend to overestimate a little bit between about 20 and maybe 80. And then we're doing really well with a few points above 100. And so in contrast to the standard products, we can actually generate realistic chlorophylls and capture those really high chlorophyll values. Next slide, please. And so just showing you what this looks like compared to the NCOS product. On the left is the NCOS product. It already looks pretty good, but again, it wasn't tuned for San Francisco Bay specifically. The middle was our new product, or is our new product. You can see that it's picking out the bloom initiation site really nicely. And on the right, we just subtracted one from the other. And so we're seeing more intense hotspots and a little bit less chlorophyll in the north part of San Francisco Bay and Sassoon than the NCOS product was showing. And so this is an example where you can take an operational product and make it better for your region if you understand your region, if you know what you were expecting to see. Next slide, please. And so getting a little bit into the excitement of what's going on in the future, looking at PACE and Glimmer, which Susanne mentioned, and also GeoXO, which hopefully is coming down the road. There's a lot of skeptics out there that say, you know, hyperspectral is not going to solve all of our problems. And so a question that often comes up is hyperspectral just hype, or is it going to be a game changer? Next slide, please. And so the hype part of it is we know that hyperspectral data is very highly autocorrelated, and that reduces the degrees of freedom and limits the number of things you can get from a hyperspectral image if you're treating it as a black box, if you're only using the satellite data. We also know, as Susanne mentioned, we can only identify globally about 13 pigments, and from that you can get 5 groups of phytoplankton. And so we are not going to be producing maps of species. It's basically impossible. There's a few species that have very unique spectral properties, but most of them, like diatoms, look like diatoms, and we're not going to tell you that it's Pseudonychia. Next slide, please. However, as Susanne mentioned, you have all those bands that you can use, and we've been thinking for a long time about what to do with that. And so this was a analysis that was done with a sensor that was on the International Space Station many years ago. And John Ryan developed this algorithm called the Adaptive Reflectance Peak Height algorithm, or ARF. And what you can do with that is you can basically pick and choose what you're interested in. And so those panels are all looking at the same image, but they're choosing which bands they want to use. And so across the bottom, we can simulate historical sensors. And so on the far left bottom is MODIS. Next to that is Maris. Next to that one is something called the Maximum Chlorophyll Index. And then on the far bottom right is John's ARF that sort of combines all of them and shows you the incredible data richness that's there. And you can start to do really interesting things with that. And so in the next slide, I'll give you an example of what you can do if you're choosing your bands. And so this is a product that Maddie Karu and Clarissa Anderson and others at Scripps published fairly recently. They were looking at these massive Lingulidinium polyhedra blooms that were occurring in the Southern California Bight, and so the Los Angeles, San Diego area. And here what you're looking at is these hyperspectral sensors also have UV bands. And Maddie proposed almost 20 years ago that if you had UV bands, you could pick out dinoflagellate blooms, because most dinoflagellate blooms are producing these compounds called microsporine-like amino acids that are very strong absorbers in the UV. And so here what you're looking at, everywhere you see those sort of red colors, that's where the dinoflagellate bloom is. And you're seeing the chemical signal of these compounds that are being released into the water. And so now we actually have the ability to do this. We've been thinking about it for 20 years, but with PACE, we'll be able to do this on a routine basis to look at these dinoflagellate blooms throughout the world because we have access to those UV bands. Next slide, please. And so getting a little bit into the hand wavy now, again, we've been thinking about what you could do. This was airborne imagery that was collected in Monterey Bay. And so we're looking at Monterey Bay and various versions of chlorophyll. On the left, all of these were collected on the same day. And so that top slice is Maris. The slice below that is Modus Aqua. And on the right is the airborne data. And I want to start just first pointing out that the Maris and Modus data don't look the same. And so even with ocean color, depending on which sensor you are using, you get very different products. And that's one of the issues we've had in the past. The right side is hyperspectral data flown in an airplane to simulate something like PACE or GeoXO. We were able to apply one of those phytoplankton functional group algorithms, Phytotext, developed by Sherry Palacios. And so that top slice, we see a patch of diatoms surrounded by a red tide, that middle slice. And then if we combine them together, we get the total chlorophyll in that bottom slice. And where that box is, that's a patch of primarily dinoflagellates that we are able to fly over repeatedly so that we could simulate a geostationary sensor. And we very clearly see the dinoflagellates vertically migrating, coming to the surface during the day. So at 9 a.m., they weren't really at the surface. By the time we get to a little bit afternoon, they're very much at the surface. And so those are some of the things that we can do going forward. And even if you can only get something like diatoms and dinoflagellates, if you understand your system, that's enough. And so in this particular case, those diatoms happened to be Pseudonychia, and they were producing domoic acid, but they were in the middle of this big red tide patch. Next slide, please. And so getting even more hand-wavy, some former NASA summer students took that data and really pushed the limits of what we could do. And so what they did is they said, well, we can actually slice vertically through the water, if you want to think of it that way. And so they took that airborne data and then they said, well, what would the spectra look like at the surface? What would it look like if you added about 7 meters of water onto that signal, and the water acts basically as a filter? And then what would it look like if you combine them together? And so if you look at the little spectra in the upper right corner, as you go from the surface down, the peaks shift around. And if you have hyperspectral data, you can watch those peaks shift around. And so that far right panel is showing you the red color is dinoflagellates right at the surface, and the green color, which might be a little bit hard to see, is more dinoflagellates, but they're down at about 7.5 meters. And if we go one more click forward, we were able to combine that. Go click again, sorry. We were able to combine that and say with high frequency radar data and with numerical model, and that data showed that the surface was being pushed up against the shore. And so that patch of red that's right up against the north shore of Monterey Bay was being basically pushed there by the currents, but the 7.5 meter water was kind of doing this spiral, and that's the water that was getting pulled out into the middle of the bay, and then they were vertically migrating up. And so we could actually see that patch move out into the center of the bay and start to migrate up through the day. And so these are sort of the exciting things you could do, again, if you understand your system, if you have enough data, and if you understand the optics well enough to start to disentangle what's going on. And so my last slide, I'll just reinforce some of the things that Susanne already mentioned. Remote sensing alone has limitations. We have cloud cover, we have covariant signals, there's continuity of sensors, they don't all look the same. The excitement is that these new sensors have higher spatial, higher spectral, higher temporal resolution. They're great improvements over what we've had in the past, but they're still limited. And to get around those limitations, what we really need is we need to put remote sensing as one tool in the toolbox and make it part of an integrated observing network. Don't treat it as a black box and expect that it's going to solve all of our problems. And so thank you very much, and I'll be happy to answer questions at the end.
Thank you, Raphe. Really, really great. So much food for thought. All right, pulling up Andrea's slides. Go ahead, Andrea. I know we're getting down for time here, so I will not rest on ceremony.
Yeah, no worries. Is it working or no?
No, it looks great from my end.
Okay, sounds good. Let me go back into that screen. Okay, great. Thank you. And thanks, Susanne and Raphe, for the great precursors to what I'm going to talk about today. I work at NOAA's Great Lakes Environmental Research Laboratory, so a little bit of a shift into NOAA's focus as well as our work on the Great Lakes. And I also shifted into a new managerial role. So I'm no longer the physical research scientist. I'm now the branch chief for the modeling group in the Great Lakes. But under that role, I'm still holding the remote sensing hat and working on feeding that data into our models in the Great Lakes. So first off, I'm going to talk a little, ooh, something happened. Sorry about that. I clicked off of it. I'm not used to using this interface. First off, I'm going to talk about how NOAA's role and NOAA's mission, in particular, the mission that was mentioned in terms of GeoXO and OCX and the upcoming mission to put that into orbit in 2032. And GeoXO fits right in between some of the other missions that were talked about here. And I'm going to talk about the NOAA mission, and then also our observing platforms in the Great Lakes and how those fit within satellite remote sensing. GeoXO is a geostationary satellite, as was mentioned already, and OCX is the next generation ocean color sensor on board GeoXO. And I know that Shelley Tomlinson is on the line, and Ryan VanderWoude, who works for their fisheries division under NOAA, and Shelley have really championed the OCX process and getting that mission up into orbit, and also really talking to users all over, international and national users, in terms of why the sensor would be important. In terms of NOAA's reasoning for why they're putting this sensor into orbit would be to really look at ocean biology, chemistry, ecology, and evaluate what's happening in the EEZ. And in our case, we would be heavily focused on the Great Lakes, which I'll talk about in just a minute here, and providing that repeat visit of 2 times a day at the hyperspectral spectral range that we're interested in viewing. And as I talk today, I'll go over some of the benefits and challenges of hyperspectral imagery. So one challenge that I'm going to talk about first is that really with geostationary data, we're able to provide more opportunities to capture cloud-free observations, yielding 2 to 2.5 times more data compared to standard observations from polar orbiting satellites. NOAA is currently relying on the 8-day composite, especially for our fisheries models and other ecosystem models, and because they need the gap-free data, and including that also the long-term gap-free data that can be available through combining multiple sensors and multiple looks. Another challenge that we face is that looking at off-nadir resolution that is provided by NASA PACE, which was presented first in the hyperspectral capabilities of PACE, we really need, especially for near-shore coastal regions and for the Great Lakes, 2 times a day visits that also provide on-nadir looking angles at regions of interest. In particular, as Raphe talked about, this is the San Francisco Bay image provided in this image. And again, this is work that has been pulled together by Michelle Tomlinson and Andrea VanderWoude, and I'm presenting this work on their behalf today. And including that, the off-nadir and at-nadir resolution issue. So GeoXO will have a 300-meter pixel resolution when it's put into orbit. The improvements that we can look at in terms of not only NOAA's mission, and under NOAA's mission, we're really looking at how we're feeding information to regional stakeholders. So we're directly looking at how better phytoplankton species and community separation could then better inform users in the Great Lakes. That's in terms of drinking water intake managers, where we draw our water directly from the Great Lakes. And in the coastal regions, it can be in terms of setting warnings for harmful algal bloom events and having better accuracy in those warnings. We can also have a better estimate of biomass, and given Rafe's example of having multiple looks from the airborne imagery, really able to look at how that biomass is transported and where it's evolving throughout the day and through that the bloom transition that happens, especially on Lake Erie on a daily basis, where it can migrate throughout the water column. We have the ability to monitor bloom patchiness and movement throughout the day, I just mentioned that, and better bloom detection around sun glint, especially if you have those multiple scenes a day. Again, I'm focusing on HABs as the intent of this talk today under NHABON, but there are also many other applications of geostationary satellites, and in particular, hyperspectral satellites. In the Great Lakes, we're going on almost 10 years of hyperspectral observations. This year is the 9th year that we're wrapping up. In the Great Lakes, this is focused on funding that we received from the EPA through the Great Lakes Restoration Initiative, but the funding we also receive is under the Great Lakes Observing System, which is connected to NHABON. They support multiple pieces of these efforts in terms of environmental sampling processors and our autonomous vehicle operations and the engineers that operate those throughout the day and night. My part has been this left-hand portion of the airborne hyperspectral imagery, and Shelley Tomlinson has been working on with Rick Stumpf on providing satellite imagery on harmful algal blooms, and then newly within the laboratory, which we just started over the past couple years, but we're able to get the first uncrewed hyperspectral flights over the Great Lakes, which I'm really excited about that, and especially with new developments of fixed wing aircrafts, which will be in-house hopefully this fall. So the point of this slide is that we know that satellites are important, and they play a key factor in what Raphe mentioned in providing a network. And in the Great Lakes, we're the perfect test bed and a test bed for transferring that information to the oceanographic community and being able to provide a small scenario of how cable networks, and including all of these types of observations and satellite data on the far left here, can be combined together to provide information, again, to users in the region or for academic use as well. And under NCOS, the division under NOAA that has more of an operational focus, I'm under the research division leading remote sensing efforts on harmful algal bloom detection, but Shelley Tomlinson and Rick Stumpf put out, and others in their group put out, a weekly, sometimes twice weekly report on what's happening with harmful algal blooms in the Great Lakes. And this example here is Lake Erie. In terms of the Great Lakes, we receive about 60 to 75 cloud-free images a year, and I have similar experience on the coastal ocean where it can be highly cloudy as well. And we've been flying beneath the clouds, taking into consideration of diffuse attenuation issues of flying beneath clouds, but being able to at least provide information to drinking water managers on the likelihood of a harmful algal bloom in their drinking water location where the intake is. And this is a trajectory of the flight path from one of our flights. So we conduct about 30 to 40 different flights a year. Those have been cut down a little bit with the operations from the drones and uncrewed aircrafts that we have in-house. And we have Resonon hyperspectral cameras. We just purchased our, I think, 5th one now. So we have quite the set of hyperspectral cameras from Resonon, and really trying to stay up to date and modernized with modernized technology. All of this imagery is wonderful in terms of the satellite data as well as the hyperspectral flights, but they do not give us any information on how toxic the bloom is. And in general, that's true for the satellite imagery that was previously reported as well. And in our region, people really want to know how toxic the bloom is. And I just received the recent report from the on-water people, which Reagan Herrera leads that effort at NOAA GLORAL here. We also do on-water sampling weekly that measures the toxicity of the blooms. But not only on-water sampling, we also combine what we see with the hyperspectral image. In this case, it's an airborne image and not the drone image, to combine robotic autonomous vehicles to look at toxicity. So we're getting that broad from the space picture, our airborne picture of what's happening on water in terms of harmful algal blooms, but also what's happening in the water at depth and providing information on toxicity. Again, this is led by Reagan Herrera, and then also in partnership with the Monterey Bay Aquarium Research Institute and NCOS, and it's under the PCM HAB project, but also partially funded under NHABON. Many years ago, Monterey Bay Aquarium, I think it started actually when I was in grad school with Raphe, developed an environmental sampling processor that they placed on a buoy in the middle of Monterey Bay. That transition to being able to detect toxins and different types of toxins. And in the Great Lakes, we've partnered with them on putting that in an AUV and then also in a bottom lander that measures toxicity and sends the information back to the laboratory. And there's a set number of samples in there in order to measure toxicity. And that's on the bottom right there. Under PCM HAB, not only have we used what they term the 3G ASP when they put it in the autonomous underwater vehicle, and the bottom lander is in the back here. This is in the high bay here at GLERL where I'm sitting right now. And but they've also pushed that to really detecting what's happening near shore. And Lake Erie is very shallow, and the funding supports recreational users and people that are still going in the water when it's bright green, and it's still highly affecting pets that are in terms of cyanobacteria blooms and harmful algal blooms, which is highly prevalent even into October, sometimes November in the Great Lakes. In addition to that, they've partnered with MBARI on putting that in an autonomous surface vessel, and that partnership is ongoing, and in coordination with also looking at what the uncrewed aircraft is seeing, and telling the autonomous vessel where to sample next for toxicity. Pulling this network of information all together, including the satellite information, I'm showing here what we have classically called the mow the lawn feature to capture what a satellite image would see, at least in a region, if we were based up in space and able to compare to what the Western Basin is seeing from an airplane. This is a combination of looking at what a three-dimensional perspective of toxin measured at subsurface from the autonomous underwater vehicle compared to what's being measured from the air from the airplane, and comparing directly those results in order to be able to tell drinking water managers, not only do we provide you surface information, but also a direct picture and image of what's happening at depth where their water intakes are located. All of this information combined together, what can be done into the future? Again, we're coordinating all of these emerging technologies in the Great Lakes and providing the perfect test bed for oceanographic instrumentation with synoptic satellite imagery, including the airborne and uncrewed aircraft systems, and up and coming, probably testing next year, hopefully, the fixed wing aircraft that has vertical takeoff and landing and will have 3-hour flight duration. But in addition to that, a cheap, easy way to monitor HABs, especially in the nearshore and the Great Lakes, are single point hyperspectral sensors that could be used in addition to the satellite imagery and our other observations. And that really would be combined with our environmental sampling processor and sensors that they're looking at in order to determine phytoplankton types and abundance, which is an issue in the Great Lakes because of clogging issues for microcystis. But combining all of those types of instrumentation into a machine learning protocol to be able to better predict and forecast when HABs occur in the Great Lakes, and that would feed into our already operational HAB forecast, which was developed partly with my group that I'm leading now. The bottom line, and this is the bottom line from Shelley Tomlinson and Ryan VanderWoude as well, that moving towards supporting national event response using all of these sensors, again, are looking at the varied spatial, spectral, and temporal resolutions on a national scale, and building that network, as NHABON has stated in their mission, is a really key factor, including our next generation satellites. Thank you. I probably have gone over. Sorry, Clisser, I couldn't see you when I was talking.
That's okay. That's okay. We're doing fine. We are coming up against the hour. We do usually schedule this for a bit over the hour to the half-hour mark, but I notice people are leaving, so I'd like to get Q&A going as fast as we can. Actually, most of the questions came in during Suzanne's talk, but any of you can address them, and I know, Raphe, you have an answer for at least one of them. But Kelly Broom did ask, how can we differentiate the sort of water column surface planktonic blooms from benthic blooms?
Yeah, so that's a good question. If you can see the bottom, you can use the same sorts of algorithms. If you can't see the bottom, then it doesn't work. You're not going to get to species, but absolutely, there's some really nice benthic algorithms for getting different groups of algae.
Thanks. Do you want to add anything, Suzanne or Andrea? No. Okay, good. So on the glimmer topic, Suzanne, I know you were showing the different regions that it can point at. West Coast was obviously one of them. So Kim Reese wanted to make sure that we can look at the Great Lakes and East Coast. I know we can. I'll let you answer that in detail.
Yeah, so I should point out that I am by no means the PI for the Glimmer mission. That's Joe Salisbury, and Antonio Menino is kind of one of the collaborators on there. So yes, that is going to be one of the fields of regard is the Great Lakes. Bear in mind that it does have a spatial resolution of 300 meters, so it's it's not Landsat-esque in its spatial resolution, but it is geostationary, so you would get 300 meter pixels if your lake is large enough for that, and of course the Great Lakes are at an early kind of temporal resolution. Yeah.
And really, that was those were the only meaty science questions. The rest were really about how willing are you to share slides This can be a sensitive topic. We do not automatically share slides post-webinar, but we do post the webinars. So if any of you out there want to share these webinars, we have a website on NHABON. We can share that now in the chat. Make sure you have it. I think that's probably more preferred than sharing slides, but you're always welcome to contact our speakers personally if you need any content that you think would be helpful, maybe for education purposes. So that's where I'll leave that. If you all want to say anything else, that's fine. All right, looks like Mark just dropped that in there. Thank you, Mark. Did I hear a voice?
Yeah, that was me. I'm happy to share slides.
Thanks. So for now, Morgan says something. She says it's an excellent webinar. Thank you, Morgan. Yes, we all miss you here on the West Coast, but we know you're going to do great work over there at NASA. All right, so I think that's a wrap. We've got a couple of slides maybe to finish up with, just some housekeeping. Next webinar, please be there. We're going to do a little dive into a regional event, something big that has happened on the West Coast this last year, and get a few great speakers on that panel to tell us about it. So please don't miss that, January 15th. Is that it, Masha? Thank you. Thanks everyone for attending. Thanks for a great panel. Those were fantastic talks. And I know I feel like everybody else when I say that I learned a lot today. So thanks.